Okay, so last time we talked about chapter one, which once again, as we sort of talked about, there's not a lot going on in chapter one. So kind of what we covered is sort of what you're responsible for out of that chapter, which is essentially kind of like the scientific method, law, theory, and that's pretty much most of it, I think. So we're now going to get into chapter two, which again, once again, these notes can be found up on Canvas if you want to use them. And this is really going to be sort of the start of the real material, unlike the fake material, I suppose we talked about last time. So in this chapter, we're going to talk about measurements. We're going to talk about how to take measurements. We're going to talk about significant figures. We're going to talk about units. We're also going to talk about really a big part of how you're supposed to sort of show your work throughout your chemistry journey, which is dimensional analysis, problem solving, how to set up problems properly with conversion factors shown to units. Then I think we will finish it up there, this chapter, with some density towards the end of the chapter. All right, so let's just start with measurements, and really a really important part of any type of measurement is the units. And the units should always be included when you take a measurement. A very simple example is if I write 100 down, right? What does that mean? You have really no idea what that means. It could mean I have $100, which is pretty good. Could mean I have 100 pennies, still not too bad, I suppose. But it could mean I got like 100 apples, which still good, I suppose. So really a number by itself is kind of useless. It doesn't give anybody any reference or frame of reference of what the sort of number represents. So we always want to include a number and some type of unit, like say centimeters. So whenever you take a measurement and you record a measurement, you're doing sort of calculations of numbers that are some type of measurement based. You should always include the units. So we really should never have sort of in this class, or probably any chemistry class you take, just kind of random numbers by themselves. In most cases, 99% of the time or more, you do need to have those units associated with it to give some people, again, that sort of frame of reference of what that number represents. Now, in terms of units, there's actually two widely used systems of units. There's the English sort of system, or sometimes referred to as the US system. And that's pretty much what we use here in the US. And then pretty much everybody else in the world kind of uses the metric system. And those are really the two major types of units that we come across. So obviously, as you can imagine, as the world got sort of smaller and people are dealing with each other, some people are using metric, some people are using the English system, there could be a lot of sort of mistakes and stuff like that. So around 1960, they had a conference on weights and measures. Sounds fun-ish, I guess. And they came up with sort of a standardized system of units, and sometimes referred to as an international system of units. The shorthand for that is the SI units. And a lot of times in chemistry or in the sciences, we use the SI units. For all intents purposes, sort of the metric system one there is sort of kind of based off the metric system, is the SI units. And we will see some conversions that go from English to metric and really back and forth. You know, if you have like your speedometer on your car, you know, they'll have like, you know, miles per hour or kilometers per hour and stuff like that, right? So that's like the metric and the English sort of system. Now, speaking of these SI units, thank you. Speaking of these SI units, these are for different types of measurements. So the kilogram is the SI unit there for mass. Although a lot of times in sort of practicality, we don't necessarily use kilograms a lot when we take measurements. We use something like grams, but the kilogram is the standard unit there for mass. Length is meters. Time is seconds, and temperature might be you're not familiar with, but you will definitely be by the time you're done with this class, and that's the unit of Kelvin. I say that because pretty much if it involves temperature in chemistry and is some type of formula, It's pretty much going to need to be put into Kelvin, and that's usually the sort of standard unit of temperature. There's only sort of one calculation that we'll probably do in this class, or most of your chemistry classes, where you won't convert it to Kelvin and leave it in degrees Celsius, but pretty much all of it is Kelvin. Also really important to understand, in addition to sort of the baseline units here, is really what they represent. So when you see a unit, you need to understand sort of what it represents in terms of what type of measurement. So when you see something like a kilogram, a gram, a centigram, something to do with a gram, which is the base unit, you need to understand that that represents a mass and not like a volume or something like that. You see something like meters, centimeters, kilometers, that represents length. Also, like volume is very common as well. We'll see liters, milliliters, those type of things are units of volume. So a lot of students sort of struggle with, they kind of put the unit down, but they really don't understand necessarily what type of measurement it represents. So it's really important to know that, you don't want to come up to me and go, and I ask you, what was your mass? And you go, it's like 50 milliliters, because that's like a volume, right? So you want to make sure that you understand, again, what those units represent in terms of what you're measuring. Now, when we talk about measurements of length, volume, and mass, as I mentioned before, the SI unit there for length is a meter. 1 meter is about 39.37 inches. Other very common units of length that we use a lot, as I mentioned, meter, centimeter, and I would say kilometer are really the top three that you probably will come across the most in terms of length type measurements. As you may like, we talk about something, some things that you do need to know, as we talked about, they want you to kind of know things and memorize things. So I would say it probably would not hurt for sure to kind of know all those guys right there. Those are some very common ones. Probably, again, the centimeter, kilometer going to be more common than probably the decimeter one. But 1 centimeter is equal to 0.01 meters. And that equals 1 times 10 to the minus 2 meters. That is a number that's written in scientific notation, which we'll talk about in just a bit, how to write scientific notation. 1 decimeter is 0.1 of a meter, and 1 kilometer is 1,000 meters. So when we look at sort of these prefixes, if you will, there are sort of certain ways things are written. So for example, 1 centimeter is equal to 0.01 meters. In scientific notation, that is really 10 to the minus 2 meters is oftentimes sort of how you'll see it, which is really 1 times 10 to the minus 2. Now, there is sort of sometimes a way to get a more larger number, if you will. That is equivalent if you divide both sides by 0.01. That will tell you that 1 meter, there is 100 centimeters. So that is the same sort of conversion. It's just found by dividing out to the other side, the other number there. So you'll sometimes see these conversions written more like kind of whole numbers, if you will, or larger numbers. And you'll sometimes, a lot of times, see them written in sort of that scientific notation, like 10 to the minus 2, 10 to the 3. Since you do and are sort of responsible for knowing a lot of these, I would sort of pick a version that's easiest for you, or that you sort of like, either the kind of big numbers or scientific notation type numbers, and kind of roll with that in terms of memorizing. So speaking of that, let's take a look at some of these prefixes. And this is what I was talking about. This is more, if you want, kind of the numberish meaning of what these times 10 to the power, or whatever it is their scientific notation meaning is. So these are some of the prefixes, and I'll be honest with you, you probably should know this table and sort of the prefixes that go with it. I will definitely say we probably will use, in this particular class, kilo, centi, milli, Maybe a little nano sort of action. As you go on to 1A, you'll probably use a little bit more of the other ones as well. You'll use micro and mega probably as you go into 1A. So you definitely probably should know this table. So make sure that you sort of know this table. But more importantly, let's talk about how you sort of properly use this table. This is probably one of the most common mistakes that people make when they go to a table like this, or they know what the power of 10 is, they use it incorrectly, and they always get things sort of backwards. So what we were seeing here, for example, if we took our friend centi, and we look on this table, and we see centi is equal to 10 to the minus 2. So that's basically what centi is. So when we see this column here, which is really the same as this column here, this is how much there is in the base unit to one of the prefix units. So this is how you properly use this. So what do I mean about base unit and prefix unit? So let's just say that we were looking at centimeters and meters. They both have meters in it, right? 1 centimeter, one's meter. Meter is the base unit. This is the prefix unit. So when we look at this table and we see that centi is 10 to the minus 2, that's how much there is in the base unit, which is there would be 10 to the minus 2 meters in one of the prefix unit, which is the centimeters. It doesn't really matter what the base unit is. So for example, if I had centigrams equals grams, there would be 10 to the minus 2 grams, which is the base unit, and one of the prefix units, which is centigrams. So that is the proper way to sort of use this table. I can't tell you how many people will flip it around and go like, hey, there's like 10 to the minus 2 centimeters in a meter, and always kind of use it backwards. So, you know, it works for any of these. So for example, if we looked at kilo, kilo is 10 to the 3. And when we do that, what that means is, for example, if I have a kilogram and a gram, and the base unit here is grams, I would have 10 to the 3 grams in 1 kilogram. Again, in one of the prefix units, that's how much I have of the base unit. Again, if we had kilometers and meters, meters being the base unit here, there would be 10 to the 3 and 1 kilometer. Any questions on that? So I say that's like super common that, you know, people always sort of go do those guys backwards when they're using it in a calculation or something like that. So for example, if nano is 10 to the minus 9, you complete this. If I have meters and nanometers, put the numbers in the correct spot, the 1 and the 10 to the minus 9. Which one should be which? Take a moment there and put it in the right spot. Okay, so again, nano 10 to the minus 9 is how much there is in the base unit. In this case, that is our base unit, as is meters in both of them. But that's meters by itself, which makes it the base unit of it. So that means that there would be 10 to the minus 9 meters in 1 nanometer would be the proper way to do that. Any questions on how to properly sort of use that? Once again, pretty much kind of know this table. I think it comes from your book. You have pretty much this table in your book. Like I said, the ones I put check marks around the kilo, the centi, the milli, the nano is probably the ones you'll see the most in our class, but you are sort of responsible for sort of the others. Any questions on that there? Okay. So speaking of the two different types of systems, English to metric, Here's a comparison. By the way, this is a ruler, right? On top are inches. On the bottom here are centimeters, these big numbers, inches up there on top. What are the little guys? The little guys are just random dashes on the ruler. Yeah. Now, those are millimeters, by the way. Yes, those are millimeters. There's 10 millimeters in a centimeter, right? So as far as 10 dashes as you go through there. So the little guys on the bottom there of this ruler are millimeters. There are certain sort of, speaking of things you should know, there are certain English to metric conversions that are considered sort of exact numbers. So for example, this is one of them that you do need to know. 1 inch is equal to exactly 2.54 centimeters. And that's one you definitely do need to know. There are a few other sort of English to metric sort of conversions. There's some other ones. So why we have it up here, why don't we pop a few of these other ones? 1 pound is equal to 453.6 grams. We're going to call that in this class an exact sort of conversion. The truth is, it's really not exact. There's a few extra digits there, but we'll call it exact for the purposes of our play here, I guess, in this class. Also, 1 mile, for example, is 1.609 kilometers. Same deal. And there's a few extra digits after that 9, but we'll call it exactly in that area. Couple other things that you probably might know. There are 3 feet in a yard, right? So those are some things that might pop up. So again, I would kind of add that to a little list of things that you should know. Any questions on that there? We're going to talk a little bit later when we talk sort of about significant figures, what an exact number is. But an exact number is sort of a number that can have as many significant figures as it wants. And when you come across an exact number, we sometimes do special things and calculations like ignore it. Now, speaking of volume, volume is the amount of three-dimensional space that's occupied by a substance. The volume is typically length cubed if you got like a cube going on there. And very common units of volume are cubic centimeters, cubic decimeters. 1 cubic decimeter is a liter. This is definitely a conversion you should know. 1 cubic centimeter is equal to 1 milliliter. They're a 1-to-1 conversion. Make sure you know that. Also, make sure you know the guy underneath, which is one that we use pretty much all day, every day. 1 liter is equal to 1,000 milliliters. That conversion is definitely something that we use a lot. And there's a couple of reasons. Very commonly, when we take volume measurements, they're in milliliters. And a lot of times when we need to use them in like a calculation, we oftentimes need it in liters. So there's usually a lot of like converting milliliters to liters done in a lot of calculations. There's also a lot of kind of going liters back to milliliters as well. So we do go back and forth between those type of units a lot in chemistry. Now, when you have something like a cube, which we'll do next week, if you take the length times the width times the height, for example, and these are all length measurements. And if you took a ruler out and you measured them in length measurements, which is centimeters and centimeters and centimeters, each of these individual measurements are length measurements. But if you multiply them together, you will get cubic centimeters, which is actually a volume. So that is a volume. So pretty much any type of cubic length measurement is basically a volume. So that's one way you could get the volume of some type of cube is to do that. Take basically 3 measurements: length, the width, the height. or the thickness, and multiply them together. So again, it's important to know that if you're talking about something centimeters by itself, just 1 centimeter, those are length measurements. Again, though, if you're talking about a cubic centimeter, that is a volume measurement, and a cubic centimeter is equal to 1 milliliter. The good news is you basically just change the units. The numbers stay the same since it's a one-to-one conversion, but they are sort of equivalent to each other. Any questions on that there? Mass is the quantity of matter that is present in an object. Matter is basically anything that occupies space and has mass. As we mentioned before, the SI unit is kilograms for mass. We oftentimes will use a guy like this, which is a balance, which is basically a scale that we use to get the mass of an object. There is a difference, by the way, between mass and weight. And the difference is one takes into account the force of gravity. One's independent of that. So when we take measurements, for example, in class, and when we record measurements on a balance, we do refer to it as the mass. And that's because, again, for example, our weight here on Earth would be different than our weight, say, on the moon, because of the gravity is different between here and the moon, but our mass will be sort of the same. So it is oftentimes confused because the process that we use to get the mass is the process known as weighing. So people think weighing, we just refer to it as the weight. So the process is called weighing, but you should usually in chemistry refer to it as the mass of the object and not the weight of the object. Now, in terms of very common ones, as I mentioned before, kilograms, grams, and also milligrams are very common units that we see. With that being said, some of these conversions we definitely should know. So once again, 1,000 grams is a kilogram. That is also the same as the kilogram prefix that we talked about on the previous page. I would also say that there are 1,000 milligrams is equal to 1 gram as well. So those are two very common sort of conversions that we use a lot here in chemistry, and you should definitely know those. Obviously, these are some other versions of that milligrams, looking down there on the table. So as I just mentioned before, again, weight does refer to really the effect of gravity. It's taken into account on that. And again, we will refer to when we sort of weigh an object as that being the mass of it. So let's talk a little bit about temperature conversions and the three sort of main temperature scales that we have here. So there's actually three temperature scales that you come across. Two of the three probably outside of chapter 2. Well, actually, I guess one of the three outside of chapter 2 you might not see very, very much. The three temperature scales are Fahrenheit, which is degrees Fahrenheit, and water boils at 212 degrees Fahrenheit, freezes at 32 degrees Fahrenheit. That's obviously the scale we use when we take our temperature and things of that nature. Degrees Celsius is sort of the metric system. Water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. We might have talked about it last time, but those are two things that you should know for liquid water or water, that it freezes at 0 degrees and it boils at 100 degrees. Those are, again, two values that are very commonly kind of used throughout chemistry as well. And we oftentimes, when we talk about sort of the boiling point or the freezing point of water, we oftentimes will refer to it sort of in degrees Celsius a lot of times. So that's usually the sort of units that we see. A third scale that might be new to you is the absolute temperature scale, but really later renamed, and most people refer to it as the Kelvin scale. One of the major differences, as you can see, perhaps, is it is degrees Fahrenheit, it is degrees Celsius. There is no degrees here. So no degrees. We don't call it degrees Kelvin. It's just referred to as Kelvin, like 273 Kelvin, 100 Kelvin, whatever it may be. We don't use the degree mark. So water boils at 373 Kelvin and freezes at 273 Kelvin. And once again, I would say out of those, probably knowing all of those would be good, but definitely you should know the Celsius, freezing, and boiling, as I mentioned before. So how do we convert between these? It is based really on where they sort of freeze and boil, and the difference in terms of temperature units between the freezing point and the boiling point for each of those. So when we look at something like Fahrenheit, it's about 180-degree difference, and it's about 100 unit difference between freezing and boiling on the other two scales. And that's what gives us our sort of equations to convert between them. So clearly they're box, you need to know, yes? So make sure you know these guys. So probably the first one here, as I mentioned before, is really the one that you're going to use the most. Pretty much all temperature sort of values when they go into some type of chemistry sort of formula does need to be in Kelvin. So converting to Kelvin is something that we do a lot. And I do need to make a correction here. And we're going to go with, they keep changing it, but they want you to use 273.2 here at this school. So we'll do that. By the way, the really true value is 273.15 is really the true value in case you see it. But here they roll with 273.2. They don't want you to do what most people do, which is 273 by itself. So 273.2 is what they use all the way through all the chemistry classes here. So we'll use it here, and that's what you should use. So you take the temperature in Celsius, you add 273.2 to it, and you then get your temperature in Kelvin. Converting from Celsius to Fahrenheit, you take 1.8 times the temperature in Celsius, and you add a 32 to it. That 1.8, by the way, is like that 180-degree difference between freezing and boiling. It also is if you learn maybe a fraction like 9 divided by 5 or 9/5. If you take 9 over 5, you get 1.8. So that is the same sort of maybe conversion you've seen before. To get to the bottom one, you basically subtract 32 to the other side and divide by 1.8. And that gives you your temperature in Celsius. And again, you take temperature in Fahrenheit minus 32 divided by 1.8. So you do need to know these formulas. And again, the 273.2 is what we will use for Kelvin. That also means if you do have the temperature in Kelvin and want the temperature in Celsius, you would take the temperature in Kelvin minus 273.2. So again, if you need to kind of go backwards, you would subtract it out going in that way. So you do need to know all these things. And we're going to talk about right now how you should give your answer when you're doing just really a temperature conversion. So if you are converting a temperature value from one unit of temperature to another, and that's really all you're doing with it in terms of the calculation, we do follow a more sort of general rule instead of really strict significant figure type rules when we're doing just a strict temperature to temperature conversion. So the general rule is this, whatever the original number looked like, the original temperature value looked like, is what your converted temperature value should look like. So what I mean by that is if your original temperature value was a whole number, when you do the conversion, you should convert it to a whole number. If your original temperature value went to the first decimal place, when you do the conversion to the next unit of temperature, take it to the first decimal place. So that's the general rules that we follow when we're doing strictly just a temperature to temperature conversion Whatever that original value was, however far the original value went, that is what your converted value should go to. Any questions on that there? All right, so we got some examples. Grab your calculator, give it a go here, do these conversions, see what you end up with. Okay, so let's take a look, see how you're doing. We'll start with the first one here. Temperature is 28.5 degrees Celsius. We want to convert to Kelvin, which again is a very common conversion. We do a lot. So the temperature in Kelvin is equal to temperature in Celsius plus, again, we're going to use 273.2. I'll get used to it, I suppose. 28.5 plus a 273.2. That is going to get us there a 301.7 Kelvin. Remember, we do not use the degrees symbol with Kelvin, so it's just capital K. Here, as I was talking about before, in terms of where we should leave our answer, when we look at it, obviously, and don't blink the screen. Our original number went to 1 decimal place. Our converted value here also goes to 1 decimal place. So again, we want to kind of keep it like the original value when we do it. Looking at the next one here, we have degrees Celsius and we want Fahrenheit. So in this case, the temperature in Fahrenheit is equal to 1.8. The temperature in Celsius plus a 32, basically. So that's going to be 1.8 times our 41 plus a 32. So we'll go 1.8 times 41, hit equals, add a 32. And that's going to give us 105.8 degrees Fahrenheit. Here, though, when we look at our original value, it is a whole number. So in this case, what we would want to do is we do want to round this. And since it's 0.8, we would round up. And we do want to round it to 106 degrees Fahrenheit and take it to a whole number. Again, making the original value and the converted temperature value basically the same. Question on that one? Yeah. Yeah, so again, what we're talking about here is specific to strictly all you're doing is taking a temperature value in 1 unit to convert that one into another temperature value in another unit. So we are following kind of loose significant figure rules here. And the reason why we generally follow this type of rule is there's a lot of variations in these calculations. Some people use like the fraction 9/5. Some people use 1.80. Some people use 1.8. So there's a lot of variations. So that's why most people will follow that general rule strictly for temperature to temperature conversions to make it look like the original number. When we do other calculations outside of just temperature conversions, there are stricter rules in terms of what you need to follow when you do those calculations. Other questions? Okay, and looking here at the last one here, we have degrees Fahrenheit, and we want to go to Celsius. So our temperature in Celsius would be our temperature in Fahrenheit minus a 32 divided by 1.8. So that will give us 160 minus 32 divided by 1.8. And on your calculator, you get like 71.111, a bunch of ones, basically, degrees Celsius. Once again, here, we're going to look at our original value, which is, again, a whole number. So we will take this guy to a whole number, which is 71 degrees Celsius. Any questions on temperature conversion? Yeah. We don't round because our original value on the first one went to 1 decimal place. So we do want to leave it at 1 decimal place. Yeah. If our original number, for example, up there was like 28 or something like that, then we would want to round because it's a whole number and we would want to take it to a whole number. Other questions? By the way, if you do need to go from, for example, Fahrenheit to Kelvin or Kelvin to Fahrenheit, you got to go the whole journey there, right? So if you have Fahrenheit, you got to take it to Celsius first and then Celsius to Kelvin. And if you have Kelvin and want to go to Fahrenheit, you got to go Kelvin to Celsius, Celsius to Fahrenheit. After, like I said, chapter 2, probably not going to see much of all of Fahrenheit, I think. So Celsius is a very common unit of temperature. It is the one we really measure with, like when you take our thermometers and stuff in the lab. So we do oftentimes take our values and measurements in Celsius. So we do see Celsius a lot. The problem with it, though, is in chemistry, like I said earlier, most of the time we need it in Kelvin to do the calculation with that value. So going from Celsius to Kelvin is probably 95% of the time what you'll do. Probably the other 5% of the time you'll be going backwards, maybe Kelvin back to Celsius or something like that. Any questions on temperature conversion? All right. So just looking at these, as we talked about a second ago as well, it's really important to understand the type of measurement we're looking at. So when I see 523 Kelvin, that is what type of measurement? That is a temperature measurement, right? When I see 25.36 liters, liters is a volume. Yep. 15 meters, meters is a length. And kilograms is a mass. So again, recognizing what those units represent is really, really important as well. There we go. Now let's talk a little bit about sort of measurements and observations. And there's two types of sort of observations that we sort of come across. One is a qualitative observation. And qualitative means that it's really just general observations about what you see. For example, it turned purple, it turned green, a solid form, there were bubbles, right, when you did this reaction. Those are all qualitative. Qualitative pretty much means no calculation, no measurement, basically. If you continue on to 1B, you'll do a bunch of experiments called qualitative analysis, which are a bunch of experiments where that's pretty much all you do is observe what happens. Like you put these solutions together, you get a solid, you get a yellow solid, you get, layers that happen, the solid disappears. There's absolutely no type of measurement. Even when you, for example, when you get to 1B and you do those experiments, even when you're actually, probably not the right word there, measuring out your solutions to do the experiment, you actually don't measure anything. You just go like, about 40 drops is a milliliter or something like that, and you kind of eyeball things and stuff like that. So qualitative is really something that's just general observations. There's no type of measurement or anything happening. Quantitative, on the other hand, is all about measurements. So quantitative basically means it is comprised of numbers, units, values. It is basically all the measurements that you make. Like you put something on the balance and go, it's 50.5 grams. That is a quantitative measurement. You take a graduated cylinder and you measure out exactly like 5.10 milliliters of water. That's a quantitative measurement. You're being very careful. You're taking an exact measurement, or a measurement, not necessarily exact measurement, but you're taking an actual measurement. So anything consisting of numbers and values is going to be a measurement. Anything more of an observation that doesn't involve numbers is more qualitative. So let's talk a little bit about scientific notation, which we sort of saw there with our prefixes. And we do use scientific notation a lot in chemistry, and we use it to handle really large numbers and really small numbers. So, if we have something like it says up there, 1 gram of hydrogen is roughly 6022000. I lost all the zeros already. I don't want to read them all. Or each one has a mass of a bunch of zeros. Clearly, if you're going to try to use those numbers in some type of calculations, there's a pretty good chance you're going to lose some zeros along the way, I would imagine. And that's not good. So we do use scientific notation to help us handle really large numbers and really small numbers as well. And in general, scientific notation has a general formula of n times 10 to the n. So when we look at scientific notation, n times 10 to the n, this first one is a number between 1 and 10. So it should not be 10, should not be 20, should not be 100. And it can be 1 in this case, but it shouldn't be less than 1. So it shouldn't be like point something. So it has to at least be 1. Shouldn't be 10. So it's got to be less than 10. So a number between 1 and 10 times 10 to the little n here. And this guy will be either a positive or negative number, depending on which way you need to move the decimal place or decimal point to get to a number between 1 and 10. So for example, if I had 1, 2, 4, 5, 6, and I want to turn this into scientific notation. In this particular case, there is no decimal point written. So usually in numbers, if it is not written, and we're doing something like this, we do assume that it's at the end here. And we do need to go one place to the left. That gives me something like 1,245, which clearly is not a number between 1 and 10. If I go one more place to the left, that's 124. That is still not a number between 1 and 10. If I go one more place, that's 12.4. Close, but still not between 1 and 10. So I do need to go one more place here to get to a number between 1 and 10. So that is 1, 2, 3, 4. So this would be 1.2456 times 10 to the 4th in terms of scientific notation. It is a positive number because I moved the decimal place to the left. Or if you want to remember it, maybe an easier way is the big numbers are positive exponents. So anything kind of above 1 is a positive exponent. Anything less than that is kind of a negative exponent, basically. Now, if I had something like 0.00432, here again, I need to go one place. Will not get me a number between 1 and 10, as that's 0.04. One more place is 0.4. So I do need to go one more place. That will give me 4.32 times 10 to the minus 3. Again, negative here because that is a small number, or I move my decimal place to the right. There is a reason, by the way, and we'll talk about it in a sec, which is why I kept all the numbers here, by the way, which you should in this case, because the short answer is they're all significant, so you should have the same significant figures. And these guys are all significant, so that is why I kept all those in this particular one. So you always just want to move it until you get to a number between 1 and 10. Clearly, if you have a number written in scientific notation, like 1.25 times 10 to the 3, and you want to turn it into decimal form, you go the opposite way. You move the decimal 3 places. In this case, that is a positive exponent, which tells me it's a large number. So clearly, if I move my decimal place to the left, that's going to be a small number, right? I got to put zeros, so we don't want to go that way. So I do have to go 1, 2, and 3 and pop a 0 in there. And we will get 1,250. Here, I do need to include the 0, so I went the correct number of places, right? And give me basically 1,250. Same thing if you had a negative exponent. Negative means small, which means I do need to move in this direction. And that would give me 0.0125 as my number. Also, when you do write a decimal that has like this, you should put that 0 in front of the decimal point. It just keeps your number clean. It also makes sure numbers don't run together. There's some delineation between each number. So you should always put that 0 in front of the decimal point when you're doing that. Any question on going back and forth? By the way, when you write a number in scientific notation like this, all of the numbers before the times 10 part is significant. And they are significant figures, really. And we'll talk about what significant figures are later, but whenever you see a number written in scientific notation, all the numbers that come before that times 10 part are always considered significant figures and are significant. So just keep that in mind. So you do need to know how to write scientific notation. You obviously do need to know how to turn it from scientific notation into a decimal sort of form. Do you have to give your answer always in scientific notation? The answer is no, you do not, unless obviously the instructions say to do so. But I will say that as we talk about significant figures and giving your answers to the correct number of significant figures, there are certain situations where there is no other way to write your answer and get the correct number of significant figures without doing it in scientific notation. So sometimes the only way you could kind of get it to the right number of significant figures is you need to write it in scientific notation. The reason that is because you really could control, for example, how many significant figures you write. So for example, if I wrote a number like 1.2 times 10 to the 2, how many significant figures does it have? It has 2. And that's those right there. By the way, this number up here has how many significant figures? It has 3, all 3 of those, right? Over here, this number has, however many that is, 5, right? So, you could write really a number, however many significant figures you need. For example, if I needed 4 significant figures for this guy, I could just add a couple extra zeros. And now I have 4 significant figures. So when you write a number in scientific notation, you can kind of control how many significant figures you kind of put there. And that's why sometimes the only way to do that is to write in scientific notation. You can't sometimes achieve it through like decimal form. So a very simple example of that is, let's just say I had 12,000 and I want to write it with 3 significant figures. Can I do it without writing scientific notation? Is there a way to write 12,000 with 3 significant figures? So if you think you could do 120, that is 3 significant figures, but that is definitely a very different meaning, right, than 12,000. So for example, the only way you could actually do this correctly is to write it like this: 1, 2, 3, 4 places. And now you will have 3 significant figures. So sometimes you'll do a calculation and go, oh, I need like 3 significant figures, and there's just no way to do it in sort of decimal form or regular number form. So you got to kind of turn it into scientific notation. Question on that. More importantly than knowing how to write it both ways is what I find most people don't know how to do is use it on your calculator, yeah, and how to punch it in properly on your calculator. So let's take a moment here and talk about how to properly punch scientific notation into your calculator so that hopefully you will do it correctly. And hopefully you've been doing it correctly. If not, maybe this will help you know how to properly do it. So first off, when you look at your calculator, you actually have an exponent button. And on most calculators, it's usually an EE button. It may be an EXP button. And then on some of the newer calculators, they have a times 10 to the n button. And usually on those calculators, you'll also have like a little wheel. I would say that these buttons usually come on calculators. They always usually seem to be 2-tone calculators, or like one color in the middle and the outside is like a different color and stuff like that. So if you have this combination, that's your exponent buttons. If you have this, that's your exponent button, and that is your exponent button. Let's talk about a couple other buttons that are important as well, and that's actually your negative button. So on most calculators, that's a plus or negative, or it is a negative that looks like that. It is not the subtract button. So those are the ones. So hopefully you can find those buttons on your calculator. And when you look at it and how you punch it in is really, really important. So we're going to talk about these 2 buttons first. And at the end here, we'll talk about sort of how to use this combination if you have that. So if I had a number like 6.25 times 10 to the minus 13, and I wanted to correctly just punch that number into my calculator to use it, obviously, in a calculation, this is how you should do it. You should take 6.25. You then should hit your exponent button, either your EE button, your EXP button. And what you probably should see on your display is one of 2 things. It should look like 6.25. It may put an E in your display. You may have 6.25. It may pop a couple of zeros up on top. May pop a couple of zeros up on top and put like a really small times 10 or something like that. So one of those sort of displays is probably what you should look at or be seeing right now if you have either an EE button or an EXP button. Now, what does that button represent in terms of our number? When you hit the exponent button, it represents the times 10 part of the number, which means that you should not hit the multiplication button. You should not be doing other things that people like to commonly do, which is like the shift log button or the inverse log. You shouldn't be using any of those buttons when you punch something in scientific notation. You should then just hit now the negative button, whichever one you have. And when you do that, it will put a negative here. It'll probably pop a negative right about there. And all that's left now is 13. And that will pop a 13. That will turn this guy into a 13 at that point. And that is the proper way to punch that into scientific notation. Any questions on that there? Now, if you have sort of that two-tone calculator that has sort of this set up as your exponent button, you just have to do a couple of extra steps because I won't say your calculator is programmed wrong, but your calculator is programmed wrong and it's going to do the wrong math if you do not do these steps. So if you do have those two buttons, the only thing that you have to do is actually pass up a print around every number that you put in scientific notation to tell your dumb calculator all together, basically. So if you have those buttons, what you need to do actually is start with a parenthesis and open it. Then you could proceed like normal and go 6.25. You could hit your exponent button. And again, your display will look like this, 6.25. It'll pop a times 10. You will have like a blinking cursor up on top of the 10. So it'll sit there and start blinking right about now. You could finish the rest of it like normal. You could hit your negative button and 13. It will then turn this into 6.25 times 10 to the negative 13. You will now have your blinking cursor next to the 13 up on top. The problem with the blinking cursor up on top is if you close the parentheses on most of those calculators, you get like a little small parentheses up there on top, and then your calculator will yell at you, you did something wrong, and you'll get an error. So this is where the little wheel comes into play. At this point, what you need to do is take the wheel, and on most calculators, hit the button there on the right. And what that will do is move your little cursor down to a regular size cursor. And now you will have a regular size cursor blinking at you. And now you can finally close that parentheses. It seems like a lot of steps, but obviously it goes a lot quicker once you know how to do it. And you'll have your number there in scientific notation. So the difference is if you have that type of calculator, you got to kind of parentheses up all of the numbers that you're going to put in scientific notation. If you don't do that, it kind of usually will separate that number out into two separate numbers, and you'll find yourself sort of with the wrong version. Any questions on that? Yeah. Probably degrees. I think it should, whatever, I think that's the normal one. So it should be okay, I think. It probably won't matter too much for what we're doing, just basic calculations. Like other questions? So yeah. Okay. So why don't we try a couple here, punching some in, we'll do some calculations, we'll see if everybody gets. And so let's take something like let's take 6.25 times 10 to the minus 7. Let's divide it by 1.2 times 10 to the 13. Let's take 4.2 times 10 to the 6 and multiply it by 1.77 times 10 to the minus 14. All right, so again, punch them in, see what you get. I'll do it as well since I made it up. Let's take a look and see. So again, on the first one here, and again, Having your calculator in degrees will be okay, probably for what we're doing. You will go 6.25 and hit your exponent button. This is a -7. So again, we're going to hit our negative button and 7. We're then going to hit the divide button and go 1.2. Once again, exponent button. Well, this is a positive exponent, so we just need to do the 13 and then an equals here. And once again, if you do have the other sort of calculator, you probably need to put some parentheses around it. If you do that on your display there, you will get, I think, here 5.208, 3. I'll write what I got going on. 333. One more 3. E minus 20. So that's sort of what I see on my display. So a couple important things when you do look at it, and a very common mistake sometimes people make with their calculators when they do this is we'll talk about why you should round in a bit, but this should be rounded to 5.2. When you do see this on your calculator, you want to make sure you don't leave that part off of your answer. So it's very common people will just write the front part and not really look to the right and see kind of the exponent part of it. That E again represents the times 10. And that is how you should write it. When you're given an answer, you should write it as times 10, not like E or something like that. So write it as times 10. And that is our exponent part, minus 20. So this would be something like 5.2 times 10 to the minus 20 would be the right answer in this particular case, rounded correctly. And we'll talk about how to round in a bit. Any questions on that? But that is a very common thing people do when they look at their answer. They kind of forget the times 10 part. You want to make sure you don't do that, that you do include it in your answer. Any questions on that? Yeah. Okay, we'll look at it afterwards. Yeah. If you find you have the sort of right front part and this part of the answer is incorrect, it is probably how you're punching it into your calculator is usually, why you're kind of slightly off. Like the front part looks great, but the exponent part looks wrong is probably how you're punching it in. Again, if you're not sure where your exponent button is or how to punch it in, just come see me and we'll find it together in a bit. Second one, we're going to do the same thing. We're going to go 4.2. We're going to hit our exponent button. This is a positive, so we're just going to go 6, and that will represent that first number. We're going to hit the times button, and now pump that in there, 1.77. Once again, we're going to hit our exponent button, which will take care of this part of the number. This is actually a negative exponent, so we do need the negative button and 14, and then equals. Once again, on my calculator display, I got going on, we'll just do this, I guess, 0.000000, and one more, 74. So here, that is probably what you're looking at. A lot of zeros. So you could technically leave your answer like that. It is a lot of zeros. Or obviously we could throw this into scientific notation of 7.4 by going 1, 2, 3, 4, 5, 6, 7, and 8 times 10 to the -8 and kind of cleaning it up in that fashion. Any questions on that? Probably the most things that people struggle with in terms of scientific notation is not necessarily just writing it, but it comes to trying to put it in correctly in here. So it's really, really important. A couple other things that sometimes will happen with your calculator is obviously, as you can see here, and we'll talk about, your calculator does not always give you the right number of significant figures, right? So you got to do a little cleanup sometimes. You want to make sure you don't forget the exponent part. And sometimes what will actually happen too is on some calculators, what will happen is you'll actually run out of space. So what will happen is it will round your calculator of all zeros and just give you like one number at the very, very end. And if you turn your calculator into scientific notation, you'll actually see some extra numbers. So sometimes if you're like, my calculator just kind of died out there at the end and just has one number. And that's a very common thing that sometimes will happen with it. It'll just kind of round because it just runs out of space if you're not in scientific notation. So if it's just a regular kind of decimal form, it will sometimes do that. Is there a question or? What? It doesn't say again?
Yeah, scientific. Like my answers are right.
Yeah, so like on the bottom one, you mean? Yeah, so your calculator, and again, everybody's might be slightly different. Your calculator might already be in scientific notation. Like for example, I could take mine and tell it to give me everything in scientific notation in terms of your answer. So that's perfectly fine. So you might even have some extra digits, like maybe like 7.434 or something like that. And that's the same thing I was just talking about. If your calculator, for example, is in scientific notation, like mine is, they might give you an answer like 7.43 with some more digits, because at that point it can move everything over and not round so much. So there, sometimes you'll see a little bit difference in those answers. Questions on that there. So definitely something you need to be able to do and type it in correctly. All right, so we sort of talked about it here. So let's take a look at some of these and put them into scientific notation. So take a moment for each of those, write them in correct scientific notation here. We need to go to the left here, one place, two places, and that will give us 5.68762 times 10 to the 2. Once again, this is a big number, so we got a positive exponent as we went to the left. Again, there is a reason why we're keeping all of these numbers, and the reason is they are all significant. And again, when we talk about significant figures coming up next, you'll understand that reason. You never want to lose significant figures as you go from sort of scientific notation to decimal place or back and forth. So that's why in this case, we actually do keep all the numbers. Here we do need to go to the right. 1, 2, 3, 4, 5, and 6, it looks like. That will give us a number of 7.72 times 10 to the minus 6. Again, this is a small number. And that is why we have a negative exponent, also because we moved the decimal place there to the right. Here, we would assume the decimal is here. So that is 1, 2, 3, 4 places. So 1.25 times 10 to the 4th. The reason we drop the zeros here, as we'll talk about when we talk about significant figures, is they're not significant. So we're going to dump them out. That way they both actually will have 3 significant figures in each of those numbers when we look at it. And lastly here, coming this way, that is going to be 1.35 times 10 to the minus 1 in terms of writing it in scientific notation. Any questions on any of those there? And again, when we talk about significant figures, it'll hopefully be a little clearer on why we got rid of some numbers, why we kept some numbers. All right. All right, we'll skip that one, I think. So let's talk a little about uncertainty and measurements. And pretty much when you take a measurement, no matter what type of measurement that you take, there's always going to be some degree of uncertainty in that measurement. And the degree of uncertainty does depend on what you're using. So for example, if we take a ruler, I'll call these centimeters, and we'll just pop a arrow right about there. Whenever you take a measurement using any type of equipment that has markings on it, there's really 2 types of markings that you want to look at when you're doing that. I personally call them the large markings and the small markings. Right? So when we look at the large markings, those are usually the ones with numbers. So when we look at the ones with numbers, that is a 1, that is a 2. So the difference between that is 1 centimeter. So each of the marked large markings there will represent 1 centimeter. We now want to figure out what does the small markings represent, which means we do need to count how many small markings we have between the large markings. Now, it's important that when you count, you should start after the previously marked large marking. So when I start counting the little dashes, I'm going to start counting here. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're going to complete your counting to the next biggest marking. So we're going to go after the first marking, stop at the next marking. Here we have 10 markings between 1 centimeter. That means each of the smaller markings represents how much? How much does it represent? 1 divided by 10 is 0.1 centimeters. Yeah, you can get that by taking 1 divided by 10 markings, basically, right? That means that this marking here is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. Any questions on that? Now, when you take a measurement, there should always be some numbers that no matter who looks at it, everybody should agree. And if you look at my arrow, no matter who looks at it, everybody should agree it is at least 1.3. And that is definitely always the numbers that should be recorded. These are all what are sometimes referred to as the certain numbers. Now, when we look at my arrow, it clearly is not 1.3. Shoot, kind of bad there. It's not really 1.4. Tilt this slant there on 1.4. So this is where we talk about uncertainty, and this is where the estimation has to come into play. So I may look at it and go, yeah, to me, it looks slightly over halfway there to the next marking. Maybe it's 6. Somebody else may look at it and go, I think it's more like halfway. Maybe it's like a 5 or halfway there. Maybe it's closer to the other side. Maybe it's like an 8 or a 9. And that is where the uncertainty comes. And this is what is referred to as the first uncertain number. We should also always record our units. And this would be the proper way to take this reading, which is 1.36 centimeters. You always want to record all of the certain numbers plus the very first uncertain number. When you do that, by the way, you record all the certain numbers and that first uncertain number, that really is what significant figures is. Which means this number, as I recorded, would have how many significant figures? Would have 3 significant figures. Yes, they would all be significant, all the uncertain numbers. Now you can determine what is sometimes referred to as the uncertainty in this measurement by taking the smallest markings and dividing it by 2. And if you do that, that will give you plus or minus 0.05 centimeters. And sometimes this measurement is recorded as 1.36 centimeters plus or minus 0.05 centimeters, which gives you the uncertainty at which you can take it. What does that really tell you? When you divide it by 2, you need to take your measurement to 2 decimal places, right? So that's basically what you need to take your actual measurement. Personally, in most cases, we will probably just give the number in front without the plus or minus, but that is sort of what it is. I will say, as you continue on in chemistry, some instructors will expect you to give the plus or minus, 0.05 and stuff like that. Any questions on that? Now, if we look at something like a graduated cylinder here, and we got 10, 20, and these are milliliters, and we put like a liquid in there. When we put a liquid in a glass container, we typically will see this curvature of the liquid. That's what's known as the meniscus. We always read from the bottom of the meniscus, and that is because what is happening is the attractive forces between the liquid and the glass is stronger than the liquid in itself. So what happens where it's in contact with the glass on the sides, it starts climbing up the walls. So it starts rising up the walls. The stuff in the middle doesn't do that because it's not in contact with the glass. And that means that if you didn't have that attractive force, it wouldn't rise, and the actual volume would be what you see in the middle. So that's why we read from the bottom of the meniscus. Pretty much 99% of the things will have a meniscus that looks like that. You probably won't see the other meniscus that kind of goes the opposite way, which is mercury. Mercury actually goes the opposite direction. You would actually read from the top. It actually comes in on itself. But that's very rare. 99.9% of the time, That's what your meniscus is going to look like, kind of a U shape. And you want to read from the bottom of the meniscus. So we want to do the same thing here. Our large markings, we have a 10 and a 20. That is 10 milliliters. Once again here, if we take a look and count our small markings, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So we have 10 markings between 10 milliliters. That means each of our small markings is 10 divided by 10, 1 milliliter in this case. So that is 11, that is 12, that is 13, 14, 15, 16, 17, 18, 19. So if we draw a little line here at our meniscus on the bottom, we know it is at least 15. That is definitely a certain number we want to record. Now we have an estimate. Maybe in this case, you feel it is actually halfway there, 0.5 milliliters. This number would have how many significant figures? It would have 3 significant figures. The uncertain number is this guy, right? Or the estimated. We could also take this and divide this by 2 to give us our uncertainty, or plus or minus 0.5 milliliters. That 0.5 milliliters is 1 decimal place, which is exactly where we took our reading to. And we could also record 15.5 milliliters plus or minus 0.5 milliliters as well. Typically speaking, you could typically go one more place to the right of the smallest marking, not 100% of the time, but if you can figure out what the smallest marking is, you could go one more place to the right. Or if you can figure out what the smallest marking is, just divide it by 2, and however many decimal places it goes to, that's how far you should take your reading to. So that's a way that you could kind of do that. Any questions on that there? All right, we'll wrap that up for today.